today. We appreciate you taking the time to join us for this immensely interesting and knowledge-based information that Andreas will be imparting to you today. Speaking to you today will be Andreas Kugelmeyer, Senior Managing Consultant, TM1 Architect. We are recording today's session, and it will be running for about 2 hours. Please note that at the top of the hour, we will take a short break and then restart the recording. If you have any questions throughout the session, please feel free to post your question in the chat box. I will be collecting all of the questions and presenting them to Andreas. So at any time, if you have a question throughout the session, type in your question and Andreas will be able to answer them throughout. Also, you don't have to dial in today, but if you would like to, just click on the little icon, the folder icon at the top left, and you'll be able to download the international dial-in numbers. We also have today's presentation available to you for download, so feel free to download it at any time. And Andreas, if you could begin, please.
Hello, good morning, everyone. Thank you for joining today, this morning in the U.S. and wherever you are throughout the world. So, yeah, we're launching a new enablement series here on TM1 and Planning Analytics, and we wanted to start off this enablement series with an overview session. I call it a primer session for that introduces proven practices for TM1 configuration, model architecture, and design to make sure that what you're building in TM1 runs fast, performs well. So this is a rather long PowerPoint. We don't have any demos in today's session. We will, however, in the upcoming weeks and months, dive deeper into some of the topics that we're discussing today, and we will also switch to other topics. So demos, samples, templates, TM1 templates as well, will be shared in subsequent weeks and months, but not yet today. So with that, let's start. So as Sophia said before, if you have any questions, please type them into the chat box. If there are any issues, type them into the chat box. The telephone lines are currently muted. All right. So what we're doing today, as I said, we're introducing configurations, design practices, and guidelines for TM1 configuration, server and database configuration, model architecture and design, and we'll also look at TM1 integration with Cognos BI. Overall, this session should provide you with the knowledge to vastly improve TM1 query processing speed, process the data faster, avoid query and processing contention, and build models that are not only faster but simpler and more user-friendly, and have TM1 utilize hardware more efficiently. So we'll start out with TM1 configuration. And that will be our first section. So we'll start with TM1 database configuration, and we'll talk about query caching, cube logging, and a little bit about cube optimization. After we've done that, we will get to TM1 architecture, general architecture and design practices. We'll discuss those, and then later on to TI processing, and then last but not least, we'll talk a little bit about considerations when using TM1 with Cognos BI. But to those sections, we'll talk later. So let's start with configuration. The TM1 database or instance configuration, where is it, how is it mainly configured, and in the TM1S config file that most of you should be familiar with. And what I'm doing here, I'm just listing the most important parameters to me. These are not all parameters that might be relevant for tuning performance, but they're the most common ones, and by my opinion, belong to the most important ones. So for improving query speed, the most important parameter would be empty queue as of TM1 10.2 and higher. That is for multi-threaded queries. We will talk about that in detail in just a few minutes. The next one would be view consolidation optimization equals 3. And that is not the default. The default is array. The view consolidation optimization method 3 stores consolidations in a tree and typically results in faster aggregation times. It's an easy parameter to test in your environment. Set it to tree, see if the system performs better. Generally, good idea to try that out. We'll talk about empty queue in the next session in detail. So for eliminating locking and contention, parallel interaction, very important. We'll talk about that in a few slides later, as well as use local copies for public dynamic subsets. A very long parameter, and we'll also talk about that later. Fortunately for both of those two, those are enabled by default. We'll also quickly talk about parameters, configuration parameters, maximum cube load threads, and persistent feeders. Those will improve your startup time, but I highly recommend to use them only if you really need to and if you build a model that's already optimized. Not a good idea to use them to really as a crutch, if you will, to make a poorly designed model much faster or perform better. So. MTQ, improving query performance with MTQ. What is it? It is available as of TM1 10.2, and it stands for multi-threaded queries. MTQ allows TM1 to take advantage of multiple processor cores, and it will to significantly increase the speed at which TM1 can perform calculations and queries. It, in essence, does so by allowing the queries to split into multiple processing threads. So that means that if it's actively employing a parallel processing regime to resolve queries significantly faster. Example is, let's say you have a query that looks at actuals, plan, and actuals versus plan. In a simplistic way, TM1 might say, okay, let me run one query that retrieves actuals, let me one query that retrieves plan, and then let me run a query that does the variance calculation. MTQ can does not only utilize physical cores, but it's also very efficient at leveraging hyper-threaded cores. Most of you may have heard of Intel hyper-threading. Most of the more modern or higher-end CPUs are hyper-threading capable. So, for example, my laptop on which I'm presenting this is has a quad CPU, but if it is hyper-threaded, it shows up in task managers as 8 logical processors, 8. So each core, hyper-threaded core, can in certain scenarios operate as if it were 2 cores, 2 logical cores. Hyper-threading, while it does not necessarily improve performance for other software or for all software, when you use MTQ with TM1, we highly recommend to enable it because it is very efficient at leveraging those cores at around 70–80% per hyper-threaded core. So it can really result in just enabling hyper-threading with MTQ enabled can enable in an almost a 100% improvement of query speed. So the performance improvement, and I alluded to that just before, of multi-threaded queries is in an approximately linear relationship to the number of CPU cores that the TM1 query engine is allowed to utilize. So the query time with empty queue is about the query time before empty queue divided by the number of CPUs for empty queue. Now, this approximately linear relationship applies to larger cubes and data volumes, and if we don't have significant involvement of leaf-level rules. Because empty queue, if you have a complex rule, TM1 will not break that complex rule into multi-threaded components. It will break subsections of the Stargate that you're querying into multi-threaded queries. So the more rules you have, the less multi-threading might be going on, okay? So as an example, a query that might take 30 seconds to run without empty queue may run in as little as 4 seconds on a quad core with hyper-threading enabled. So that would mean 8 processing units, okay? Now, if you have smaller TM1 models with high rule complexities, empty queue may not result in significant performance gains. But it's not a good idea to count on empty queue to offset the effects of poor rules or cube designs or really, really complex models. Empty queue, I'd say, allows us to build massively large models now and actually have really good performance. But we still have to be careful about how we design the rules and feeders and all of that. Now, why does it not result in significant performance gains if you have small models and, let's say, very much rule complexity in there? It's simply because if you have a very small model, the overhead of processing the multiple queries might just not be enough to, or might be too large to actually make a difference when you're running a small data set query in empty queue mode. So, configuration basics for empty queue. How do we enable it? The empty queue value in the config file specifies the total number of CPUs that TM1 can leverage for empty queue. Important is empty queue parameters are dynamic. In other words, the TM1 database process does not have to be restarted after changing the empty queue settings. That's good, obviously, because you can test with your empty queue settings and you don't have to restart the engine. Configuration options, we have a few here. Empty queue equals n with n the number of CPU cores. For empty queue equals 1 or equals 0, there is no, or if there is no empty queue entry, there is no empty queue. That would mean it's disabled. So 0 does not mean unlimited, it means no. Empty queue all, case insensitive, means use all available processor cores. Empty queue minus n, and so use a formula m minus n plus 1, where m is the total number of CPU cores. And so what you could do here, you could use this minus n formula to, for example, say use all but leave 4 left or leave 5 left or something like that. This makes sense if you do need to ensure that there's processing cores available for non-TM1 database server applications, such as TM1 Web, for example. Another good parameter to know about is the operation progress check skip loop size parameter that specifies the number of cells to be processed before checking whether multi-threaded splits are needed. So in other words, what TM1 will do, it won't multi-thread everything. It says, oh, if this is a small query, I won't even try to. So it's a small query, I'm not going to split that. One can, however, change this parameter. I found with the applications that I've worked on in the last few years that very, very rarely did a change there really make a difference, but it's still a parameter that is available, so keep that in mind. You can also use the immediate check for split, set it to T, that effectively sets the operation progress check skip loop size to 1. So it will immediately check for a split in that case. Keep in mind the parameters are dynamic, so it's easy to test and evaluate. Now, okay, a lot of parameters, and where should I start? Our recommendation is set empty queue to all or empty queue to -1, which means it's effectively the same thing, or empty queue equals M, with M meaning the number of CPU, logical CPU cores, including the hyper-threaded cores. In other words, all logical processing cores. Why set it to all? Get to that to the next slide. The only reason why I would not set it to all is if you have slightly smaller TM1 environments, you want to use empty queue, and in those smaller TM1 servers, you might have TM1 web on the same machine as your TM1 database server. In large enterprise production environments, this very rarely is the case, but if you do have TM1 web running on the same machine, and most of you know TM1 web is CPU intensive, the old TM1 web more than the new TM web, but you still need some CPU, then you might consider reducing the empty queue value by the number of CPUs you want to reserve for those other processes, but for TM1 web in this case. So empty queue to all, a question we get a lot on that. So, well, but if I set empty queue to all, and one user or a couple users run really long, big queries, won't that hog the CPU? How about all the other people? It's a very good question, and it's a concern I had initially when empty queue was first introduced. Fortunately, we don't have to worry about that. So we don't have to worry about it because TM1 will continuously align the CPU utilization with concurrency. And we'll just talk about that, and then we'll answer some questions that popped up here. So what happens with empty queue, what TM1 does, it deploys a give and take approach to assigning and reassigning processing units. So TM1 will continuously balance and rebalance CPU utilization between threads using empty queue. So what that means is, let's say you have all CPUs are available and a particular query can leverage all CPUs. So TM1 may assign the maximum number of worker threads available and start empty queue processing with all cores. Now let's say another query is run, or other users are running query at that time, and they suddenly request CPU time. TM1 will then take CPU processing power away from the first query and assign CPUs to the second, third, fourth, fifth query. So what you will see if you monitor empty queue, and we'll talk about that in just a few minutes, couple minutes, that if you start out and you monitor empty queue, and let's say you are having a production box with 16 CPUs and you're running this massive query, and you'll see all 16 CPUs are engaged at 100%, which is good, meaning we're actually now leveraging hardware as much as we can. The moment you launch other queries, you might see, if you monitor this in TM1 Operations Console, that suddenly the threads for the first query get reduced to, let's say, 4 or 5, and the other threads, the other users are leveraging CPU activity. So it's continuously rebalancing. So before we get to memory, let's go to the question. So we have a question here. As empty queue allows multiple cores to participate in query calculation, is there a way to allow multiple threads to participate in TI process calculation? TI processes appear to always use only one core when processing data. That is correct. is through TI, a TI thread will only process one core. However, if you do query a value through a TI process, you do a cell get n, for example, in the context of a TI. If that cell get n were to, let's say, have to consolidate a very, very large number of values, and empty queue would apply, it would, in that case, employ empty queue as well. So there's a second question. It says, implies exporting a rule-heavy cube to a static reporting cube if possible. I do not understand the question, I'm afraid. Please post again and or explain it in a different way. I apologize. So and what's really important to keep in mind when you're using MTQ is that you will need more TM1 server memory. Not much, probably 10, 20%, it depends on the instance. But what that means is subsequently it requires you to re-optimize the VMM cache configuration. If you haven't heard about VMM, we'll talk about that later. So, but what we need to talk about is, or what we want to make sure is that, let's say I run a long query, and that query employs all CPUs, and I'm running this query on a reporting cube that, let's say, gets updated once a day, and it's massive. Okay, let's say this cube is massive. We've had queries run with MTQ, run really fast on cubes with over 1 billion facts, populated facts. Let's say this query is massive. It's this large cube. It runs in the top-level consolidation. Let's say it runs in 20 seconds, but it requires, let's just say, 16 CPUs. So if I were to refresh that query, just hit refresh either in TM1 Web or CubeView or Planning Analytics Workspace, I don't want that query to fire up again and launch all these CPU activity. I want that data to be cached. So that's why we need to reconfigure VMM so that such that VMM is large enough that the cube data, the query data, is cached. MTQ monitoring, use TM1 Top or Operations Console with MTQ. What you will see is that we here have this thread. The ID is 14744. We have a query that is run. You see it's a rule, and it does apparently some FX calculation here. And you can see here that this employs 6 worker threads. Work thread 4, it's difficult to see, but you might be able to read it. It says work thread 4, 14744. So it's the work thread for the query thread that I'm running. Now, what you'll see if other people are launching, you will see the number of these work units increase and decrease depending on MTQ needs, depending on the query, and depending on activity of other users. That's that rebalancing that occurs. A little, just very quickly on MTQ logging. There are various very useful logging features available to log MTQ. Stargate logging is helpful. Parallel debugging, the parallel debug flag is helpful, and operation thread debug. So this allows you to do very thorough debugging and troubleshooting of MTQ capabilities. I will not get into the details of this. I just wanted to have it in this PowerPoint. We will have a separate detailed session with demo and all of that on MTQ, not today, obviously, where we will cover this in detail, okay? Same thing here. Please only leave MTQ debugging on, debug logging for debugging and troubleshooting. Okay, it will create very large log data files, so only use it for that. And if you want to test and compare performance of different empty queue configuration scenarios, and you really want to have documentation on query times, you can just put Stargate debug logging in there, and would tell you how large the Stargate is, how long it took for the Stargate to be created. For lighter, strict monitoring of empty queue, I'd use Operations Console or empty queue, or TM1 Top. There's another question here. So this is the question on, or a revised question that on static reporting cubes. If empty queue isn't efficient at n-level rules, you have a n-rule heavy cube. It seems like it would help, if possible, to export rule-heavy cubes to a static rule-light cube to assist reporting and optimize empty queue usage ability. Yes, maybe. It's not that empty queue isn't efficient at n-level rules. It's just that a leaf-level rule is not broken down into multi-threaded components. So if you have a rule-heavy cube, the more rules you have, or the more cells are affected by rules, the less easy it is for the empty queue engine to break the query into multiple components. So when I gave you the stats on empty queue performance gains, it was important for me to point out that if you have a lot of the rules, you won't get, adding another CPU or increasing the number of CPUs by 2 won't cut your query performance by 2. So empty queue still makes a huge difference with a lot of leaf-level rules. It still won't be as linear, okay? So I would not build my models differently with empty queue, except that I now use rules much more often, because I know that even in larger models with empty queue, I might be getting just exceptional performance out of it. In larger models, I mean very large models. Now the question that we often get after people understand that we'll run queries faster is, can I use it to speed up TI processing? The short answer is no. Yes, you can use the view construct command against the source cube and the view, and that, yes, will trigger empty queue as needed. So if in the prologue of a TI, let's say you build the view, if you execute a subprocess like the one that we see there, where you're using view construct on the view, that will trigger empty queue. However, that will construct the view if you query it as a user. A TI process processes views differently in the metadata and data tab. It doesn't really access a view, a Stargate, the same way you would when you query it. So it's a little bit different of how a TI process goes through a view in the data tab. So view construct there by my tests is not really helpful, not in an empty queue context. The other thing you want to think about if this were to work, it's just a general caveat on using view construct. Some views may just be too large to warrant caching for view construct. Because view construct will cache the view, but only if VMM is large enough. And if you have massively big cubes, you might just have to increase the VMM cache correspondingly, which might just be too much. this is the end of the section on empty queue. Again, we will have a detailed session on this at a later time, where we'll demo and we'll look at the logs, and we'll take a look at how we can do debug logging, how we read those, and so forth. Parallel interaction. Parallel interaction is available as of TM1 952, and it's a database server configuration that improves response times of writing data by removing lock contention resulting from concurrent queue data access. So when you enable parallel interaction, it changes the TM1 object locking model so that write operations are not blocked by read access or write operations to the same queue. It is enabled by default. I have not seen anybody disable it. Really, just keep in mind that if for some reason you come across a TM1 model where parallel interaction is explicitly set to false, that would be rather unusual, and you might want to investigate why that is the case, if that was just a mistake or so forth. Use local copies for public dynamic subsets. It's available as of TM1 10.1 and higher. Prior to that TM1 version, using MDX subsets would lead to a significant lock duration on the TM1 server side, which led a lot of us to not build MDX subsets, or what we would do, we would construct MDX subsets, let's say on server startup, and then turn them into a static subset and all that. Now, with this new parameter, when using dynamic subsets, the TM1 server uses really quote-unquote local instead of server-wide copies of the MDX subset when possible. Doesn't mean it does anything on the local client machine. It's really the local thread, the local in TM1 server environment. And that means the locks are generally, to a large extent, avoided. So as of that version, I highly recommend to use MDX subset, especially because compared to static subsets, they're typically faster to construct and easier to maintain. Obviously, if you do have a very small model and very small dimensions, excuse me, the performance difference when constructing subsets with MDX or not might not be that big, but the moment you get to dimensions that are many thousands or even into the millions of elements, if you try to build subsets without MDX, it takes a very long time. So MDX subsets are generally the best way there. Caution there, keep in mind that an MDX subset is constructed each time you call it. So in cases when you're referencing a dynamic subset in the data tab of a TI process, let's say, using subset get element name, or you're looping through a subset anywhere in the TI, then it is best to build the MDX subset as needed and then convert it to a static subset prior to referencing it. So let's say you have an MDX subset with 100,000 elements, and you're looping through it in the context of a TI. Sometimes we have to do that. That would mean the subset will get constructed each time you use subset get and subset get element name. Performance would suffer very, very drastically. So in that case, build it as MDX, an MDX subset, but turn it static. Now with TM1 now has a newer function. It's called subset MDX set that allows you to do that in one step. So you build a subset through MDX and immediately set it to be a static subset. Keep in mind that this parameter here, use local copies for public dynamic subset, is enabled by default, right? So make sure it's not set to false. Maximum cube load threads. We're now getting to reducing database instance startup time. By enabling maximum cube load threads, the TM1 DB configuration allow, in the TM1 database configuration, you are allowing it to use multiple processor cores to be utilized on startup of the database. So that allows TM1 to essentially process load cubes in parallel and process feeders in parallel. It will consume more memory because you may have duplicate feeder processing, right? So you might be launching cube A, loading cube A, and that might already have feeders into cube B, and you may do that in parallel to loading cube B, for example. So my recommendation is use that only if needed. Do not put in place by default. If you do need it, start with 50% of the number of available processor cores and evaluate the trade-off between increased memory consumption and reduced startup time. Similar with persistent feeders. Persistent feeders allow you to improve the reload time of queues with feeders. So with persistent feeders, the feeders for the cube rules are saved in a feeder file that then will allow you to start up the database instance within really only very few minutes, even if you have an incredibly large amount of feeders. So the feeders are saved when the data is saved or rules are edited. So persistent feeders, yes, they do allow you to cut down TM1 database startup time by an order of magnitude. I would, however, again, only recommend to use the persistent feeders parameter when it's really necessary. Build your model without persistent feeders on, so with it set to off, which is the default, should be the default. And optimize feeders and rules such that ideally you do not need persistent feeders. If you still find that you need persistent feeders or you want to increase startup time, put the parameter in place after you know that you have built or optimized the cube rules and feeders as well as you can. Query caching, VMM and VMT. So query caching behavior in TM1 is configured per cube through the VMM and VMT value in the cube properties cube. So VMM defines the maximum amount of memory to be used for caching of Stargate views per cube. Let's really think of this as the memory pool in RAM that's made available for caching. So if you don't specify a VMM value, it will take the default, and that is only 128 kilobytes. So with 128 kilobytes, that sounds like very little. You can actually cache a little bit with that. Just keep in mind it only really stores the data that's the result of the query. But the problem is that the cache will be full pretty quickly. TM1 will not purge old cache unless you change a value in the cube. So as long as the cube data stays the same, old cache data is not purged out. So once you reach 128, it just won't cache anymore. Okay? So my recommendation there is set for your main cube, set VMM really high. Okay? We'll talk about recommendations on the default value soon. The VMT value defines the query time threshold as of which Stargate views, there's a typo there, will be cached. The default is 5 seconds. I typically leave it at 5 seconds. If something runs less than 5 seconds, I don't bother caching it. So the Stargate views that it caches is really the calculated and stored subsection of the cube that's created when you query the cube. Okay? So it's not the same as a view object. It only contains the data for that defined section of the cube. No formatting in it and so forth. So where do you start with VMM and VMT? It's debatable here. What I do, I set the VMM value to a new default, quote-unquote default value of between a megabyte and 5 megabytes. So that will allow caching of relatively large as well as many views and improve performance accordingly. Okay? For models that are highly volatile, in other words, for cubes that change, where the data changes a lot, this might be a perfect setting or a good setting. You make sure that larger queries are cached, and that's all, because every time the underlying cube data is changed, the cache will be entirely purged. If you have large reporting cubes that only get maybe updated once a day or once a week, it might make sense to actually set that cache even higher. So you really cache everything you possibly can. Depends on the data volume too, right? It's all a matter of how long or how well does this model perform anyway. Now, with empty queue, VMM needs to be higher, significantly higher. So we saw this TM1 Operations Console image before, the screenshot before that showed the operations threads that are started with empty queue when you run a query. What you want to make sure is that when you test your sample queries and you configure empty queue, that yes, you will see the empty queue threads, but then when you hit refresh, you do not want to see those anymore. So you want to see the multi-threaded query engine kick in the first time. But if you hit refresh, you only want to see one row in TM1 Top Operations Console. If you do not see that, if instead you see again the 4, 5, 6, 7, 8 or more processes, that means that query couldn't be cached because the cache is too small. So in that case, increase VMM. This is important, especially for large models, right? Really large scale data models. If you say, oh, I will build this, I will implement this model in TM1, and now with empty queue, I have, let's say, a production box with 16 CPUs. Yes, I can have millions and millions, hundreds of millions, or billions, actually, of populated leaves, and it will perform well. Yes, it will. Just make sure you configure the cache well enough too, so you're not just using up CPU time for no need, even though you really don't want to. You don't want to employ all CPU capabilities of the machine just when a user hits the refresh button, but the data hasn't really changed. Question here is, any downsides to setting a high VMM value? No, I wouldn't say so. You need to have enough memory available, right? So if you have a large, let's say your TM1 model, if you just started up is, let's say, 30 gigabytes, right? Among those 30 gigabytes, let's say, are mainly due to two large cubes that are each about 10 gigabytes in size, right? So if you set the VMM cache to 4 gigabytes, which is the max per those cubes, you need to make sure that you have that memory available too on the on that server, right? Cube logging. So TM1 data that is loaded or entered into a cube is not automatically committed to disk, the cube file, but it's retained in memory only. So for cubes with cube logging enabled, and that's the default, data changes will be logged in the TM1 server log file, the TM1 slog file. You can disable cube logging for a particular cube by setting the cube's logging value and cube properties to null, as we see in this screenshot here. So first of all, when we talk about logging and saving data, keep in mind, use cube save data to commit one cube's data, or use save data all to commit all data to this. So keep that in mind. There's the cube save data functions. You don't always have to use save data all if you want to commit data to this. Now, speaking of committing data to this, do we have to do that for as long as we have logging enabled? We don't really have to do that all the time, right? Because the data is logged, and if TM1 crashes or somebody stops it but shouldn't have, when it starts back up, it will retrieve data from the log file and restore the data as it was before. So that being said, we know about save data all and cube save data that will require a write lock on the cube database. So it's not recommended to use save data all and cube save data at the end of each TI, because you don't need to do it, and it will cause potentially lock contention. If you have very, very large cubes, this might take a while to save this data. So logging is important. So up to the chase here, for larger read-only cubes, it's a good practice to actually disable cube logging, because it will speed up data load performance. That, of course, would only be when they're really large, if you don't update them too often. If this large read-only cube is updated all the time, that depends. It really depends on the use case there if I would disable cube logging. But if I update it once a day, I would just disable cube logging and do a save data all, or just a cube save data at the end of the update procedure. It's a read-only cube, so it can't be accidentally overwritten by users, so you don't really need cube logging for audit purposes, right? And because you update it only, let's say, once a day with, let's say, a certain set of actuals or GL data, you know that if you do have an outage, you know exactly how to restore that data. Something goes wrong. But for any planning, budget, forecast, any other input cube, you should always have cube logging enabled to allow for proper auditing to occur and to allow for data recovery in case of outages. You know, software at times crashes. We don't want to lose data. Losing data is the worst thing. That makes people very nervous, and it causes a lot of work for the end users and for the TM1 admins. Now, a lot of times you see people do the following, and you sometimes see this in, IBM. We will sometimes put this code in place. It depends on the use case. We will build a TI that automatically and temporarily will disable cube logging during data load, but then re-enable it after the load. Now, there's a big caveat with this. I personally do not do this because of this caveat. If you put this code in place in the TI process and the TI doesn't complete, let's say you have error logging in there and there's a process quit that you execute, or it's a fatal error or crash, or the thread is canceled by an admin, or the TM1 server is shut down. If this happens before the epilogue is run, the cube logging will be disabled for the cube. So let's say something bad happened, server crashed, server was back up, everybody thought it was fine. Suddenly, let's say you did this on a forecasting cube, but nobody thought about that cube logging might actually be off. So now cube logging is off, people enter data for a day or two. Say there's a TM1 bug, that's really what's caused the initial crash, server crashes again, and all the data is lost. So if you feel you want to reduce the log file data volume, and that's the reason why you're disabling logging temporarily and enabling it again, make sure you have a chore or some other process in place that checks regularly if cube logging is enabled on those cubes. And if not, re-enable it. I personally just don't disable it. So I make, and again, that's debatable. I'm not saying that this is the best practice. This is what I would recommend. Say, leave it on for cubes that should have logging enabled, and for cubes that do not, turn it off. It can lead to larger log files, and yes, it's sometimes a little harder to audit the log files because you're saying here, I have all this information in here from my actuals update, and I didn't really want that in my audit, but I feel it's just safer and simpler. And now we're getting to the optimization of internal cube dimension order, cube optimization. So the order of dimensions significantly affects cube memory requirements and query performance. And the effect on query performance tends to be larger than the effect on RAM utilization. So at the same time, the relationship between memory and query performance is not linear. If you reduce your memory by 20% by having a better cube dimension order, that could mean you're getting over 1,000% improvement in query speed. It could. So you want to look at cube optimization as an essential tool and procedure, possibly recurring, so not just do it once. How do you determine the initial dimension order when creating a cube? Well, I'd say don't worry about the performance impact of the dimension order when you create the cube. Optimize it later. We'll talk about that in the next slide. You really want to pick a common dimension order for all cubes of a TM1 model, simply to improve usability. So if you say, my entity dimension should always be number 1, put it always number 1 if the cube has entity, right? For example. Or time dimension should always be after the version scenario dimension, for example. Right? Pick the same order and stick to it. So then later, when you have a representative data set, right? There we go. The line wasn't proceeding here. So how do you optimize the cube dimension order? So the cube optimizer lets you rearrange and evaluate a different internal order of the dimensions in the cube, and it allows you to apply the new sort order to the cube if desired. It will not affect any TI processes you built, nor rules. So you don't have to change queries, you don't have to change rules, you don't have to change TIs. The internal order of the dimensions is independent, okay? But it will make the cube faster or slower, or use more or less memory depending on how you internally order and sort those dimensions. So the actual order of the dimensions in the cube structure not change. It changes the way they're ordered, the dimensions are ordered internally on the server. So you can have TM1 itself evaluate the cube structure and determine a system-generated optimal dimension sort order, or you can manually do that. Now, on system versus manual, I tend to start with system and check what system tells me or recommends, and then I take it from there and perform manual improvements if possible. Well, we have some bullet points here on a recommended approach. You want to group your dimensions into sparse and dense dimensions. Generally, the smallest sparse, so generally the best order is smallest sparse to largest sparse, followed by smallest dense to largest dense. Now, here's an exception. It's typically better to put a very small dense dimension before a very large but sparse dimension. So if you have a version dimension but you only have 2 or 3 elements, that tends to be much better positioned before a very large but sparse dimension, such as product. Or you have a currency dimension, but that cube only has US dollars. Also very different. But you might have hundreds of currency in it, but only USD is populated. The TM1 manual says you only should optimize the order of dimensions in a development environment. Well, think of this as follows. Yes and no. You want to determine the optimal order through testing in a production-like dev environment, because you want production-like data item. Then at a time of zero concurrency, you want to implement the tested new dimension sort order in the production environment. So you don't migrate really this optimized cube. You might actually go live, and then a few months or half a year later, you might use a copy of production, do your tests, determine possibly a better dimension order, and then don't migrate that to production, but apply the dimension sort order to the production environment when needed. Now, if a dimension, such as a measures dimension, contains string elements, it needs to be the last dimension. Now, a lot of us put a comment measure into the last dimension, the measures dimension. Comment for strings, string comments. A lot of times, we don't really use those comments. If we don't use the comments, but just put it in because, remove the comments. Because the moment you do, you are free to move that dimension. Now, very often, moving that measures, that last dimension, if it doesn't include string elements, moving that upwards from the last position can result in significant memory savings and performance gains. Why is that? Typically, a measures dimension only has a few measures. It tends to be quite small and dense. Now, the TM1 system-generated cube joiner optimization will never consider moving the measures, the last dimensions. It will just not touch it. So that's one key aspect where doing this manually can make a huge difference. So on measures, dimension, and comments, what I, for example, do, if I have a large forecast input cube and that cube has comments in it, and I'm having performance problems or I want to see how I can improve performance, I might remove the comments measure and test. This is in the test environment. And if I can get significant performance and memory improvement, I might say, okay, this cube can run much faster if I don't have string values in it. What I'll do instead then, I will build another cube that's identical, but is only used for string comments. And I then, you integrate the two cubes through TM1 Web, right, to the user. It's seamless. So keep that in mind. Don't just put string elements in there by default, or if they're not really needed. Obviously, if this is a very small model, this doesn't really matter. But the larger the data volume, the more relevant this may become. All right, so we're going to go on now to section 2, and I'd say we take a quick break, and we'll be back in, like 4 minutes, 5 minutes. Sophia, what's your?
Yeah, give everybody about 2-3 minutes.
Okay.
We'll be back at 10:05.